Now let us continue with the classical experimental approvals of general theory of relativity. From the Newton's seminal solution of Kepler's problem, it is known that planets orbit around the Sun along ellipsoidal trajectories, and we want to see now how this behavior is changed if we take into account corrections from general theory of relativity. To do that, we want to find the r as a function of phi, so the curves which are covered by the particles during the planets or particles, point-like objects which orbit around a gravitating body. So to do that, let us do the following. So let us consider dr over ds and write it as a dr over d phi times d phi over ds, and this guy can be expressed with the use of, so this is dr over d phi, and this can be expressed with the use of the conservation law as L divided by mr squared, and then this can be written as minus L over m du over d phi, where we have introduced the notation that u is equal 1 over r. 1 over r. So then, using this new definition, the equation for the geodesic, which was using dr over ds, can be written as follows, as du over d phi squared plus u squared times 1 minus rg times u equals to e squared minus m squared divided by L squared plus m squared divided by L squared rgu. So this equation is equivalent to the one that we had dr over ds squared. Well, let me write it explicitly. Dr over ds is equal to e over m squared minus 1 minus rg over r 1 plus L squared divided by m squared r squared. So this equation is equivalent to this one in the new notations. Now let us differentiate. Let us take differential of both sides of this equation over d over d phi. So take differential of this equation over d over d phi and divide it, after obtaining the expression, divided by du over d phi. So we divide by this, both sides of this equation. As a result, we obtain the following equation. Du squared over d phi squared plus u is equal to m squared rg divided by 2l squared plus 3rg over half times u squared. So this is the equation we are going to work with. In this equation, one has to bear in mind that rg over r, which is nothing but rg over u, is much less than 1. Because, in fact, we want to consider this equation as a deviation from the non-relativistic limit. So in this is non-relativistic limit when this is much less than 1. In this limit, this term is small in comparison with the rest of the terms in the equation. So in this limit, we can neglect this term. So this is a Newtonian limit of this equation when this is much less than 1. The Newtonian, let us see that explicitly. The Newtonian limit of this equation is as follows. So as we're going to do the following. We're going to consider u expanded as a perturbation, u0 plus u1 plus etc. So this is a leading term which solves this equation without this term. And this is a perturbation over this due to corrections coming from this term. So let us consider leading contribution Newtonian equation, Newtonian limit. So in this limit, this equation reduces to the following one: du0 over d phi squared plus u0 is equal to m squared rg divided by 2l squared. So this equation is oscillator type equation because this is just in homogeneous part. If it were 0 on the right hand side, we would obtain just oscillator equation. With non-zero this guy, we have just in homogeneous perturbation. So then the solution of this equation is nothing but the following. U0 is equal to, well, we can easily solve oscillator equation. U0, which is by definition is 0, where subscript 0 corresponds to the Newtonian limit when we dropped off this term. So in this limit, we have the following situation, that m squared rg divided by 2l squared 1 plus e cosine phi. So where e is kind of integration constant, which follows from this equation. So this is the amplitude. Anyway, if e, which is called eccentricity, if e is less than 1, if e is less than 1, this e is less than 1, then this thing is nothing but the ellipse. If e equals to 1, we have a parabola. If e is greater than 1, we have a hyperbola. So these are three types of motion in the central central Newtonian force in classical mechanics. But the closed trajectories, which are of interest for us, correspond to e less than 1. In this case, this is just ellipse. Indeed, then we see that when we drop off this term, we reproduce the Newtonian limit, which corresponds to this situation. Now, we want to consider the perturbation for this. So for this reason, we want to plug this thing, this expression, approximate expression here, and find the equation for u1. So to find the equation for u1, in this term, we have to take into account of only u0. Then, for u1, we obtain the following equation, d squared, well, taking into account this equation, obeyed by u0. For u1, we obtain the following equation, that du1 over d phi squared plus u1 is equal to 3/2 rg times u0 squared. So this is easy to see. We took into account u0 in this term only. So this is the equation we obtained for u1. Well, this is a relativistic general theory of relativity correction to Newtonian trajectory will follow from here. We want to find the biggest contribution to u1 following from this equation. This equation is very similar to the following one. So we have oscillator plus external force. So external force may cause a resonance on the left-hand side. That will be the biggest resonance contribution to u1. So our goal is to solve this equation and to find biggest resonance contribution to u1. So we are solving this equation, d squared of u over d phi squared plus u is equal to m squared rg divided by 2l squared plus 3rg over 2u squared. We're solving this equation, which is exact in the non-relativistic approximation, so consider this term as a perturbation. And so we are looking for the solution of this equation as u0 plus u1 plus dot dot dot. And at this level, we restrict ourselves to these two first terms, where u0 solves this equation, d squared u0 over d phi squared plus u0 is equal to m squared rg over 2l squared. And then for u1, we obtain the following equation. It is just d squared u1 over d phi squared plus u1 is equal to 3 rg over 2 u0 squared. So we can see, we want to look for the solution of this equation when this is considered as an external source, and we want to see for the biggest solution of this equation. So let us see what is this, and we found the solution of this equation, as we found, is just u0 is equal to m squared rg divided by 2l squared 1 plus e cosine phi. So having this, let us look at this term. So this term, 3rg over 2 u0 squared, if we substitute u0 here, this guy, and reshuffle it a little bit, this guy is equal to 3rg cube m to the fourth divided by 8 l to the fourth 1 plus e squared over 2 plus 3rg cube m to the fourth 4l to the fourth e cosine phi plus, so let me, plus 3rg cube m to the fourth divided by 16 l to the fourth e squared cosine 2 phi. So what does this term do? If we add this to u0, this just leads to the shift of this term in this equation. So this is just a correction to this term, or to this term in this equation. This correction, what does it do? It changes just the biggest axis in the ellipsoidal motion of the planet. This axis is not measured with such a precision that we can observe the presence of this term. So we just consider this term as irrelevant and neglect. Now, this term and this term are behaving as external force in this equation, as external forces in this equation. And we want to find the biggest solution of this equation. The biggest is the resonant due to the external force. But then this term, due to the mismatch of the frequency between 2 and 1 here, due to the mismatch, doesn't lead to the biggest resonance solution, while this term does lead to the biggest resonance solution, because this force is in exact, the frequency of this force is in exact agreement with the frequency of the oscillator. So our goal then is to find the resonance solution of the following equation: d squared u1 over d phi squared plus u1 approximately is equal to 3 rg cube m to the fourth 4l to the fourth e cosine phi. So we want to find the resonance solution of this equation. To solve it, we're going to look for the solution in the following form, as a of phi times sine phi plus b of phi times cosine phi. After substitution of where we consider this as slow functions of phi. So this is the ansatz for the solution of this equation. We're going to substitute here and find the equation for a and b. That's not very hard exercise. Not a very hard exercise. The equations for a and b are as follows. So a double prime is equal to b double prime is 0, where double prime is just a second differential with respect to phi. And we have the following equation, that 2a prime cosine phi minus 2b prime sine phi is equal to 3rg cube m to the fourth over 4L force E cosine phi. So from these equations, one can easily see that B prime should be 0 and A prime should be 3Rg cube m to the fourth divided by 8L to the fourth E. So as a result, B is constant, and one can see from here that this is not a resonant solution. If B is constant, this is just oscillatory solution. From here, we find that A should be linear function of phi. Then, while substituted here, we have a resonant, exactly resonant solution of the equation. That's what we have been looking for. This is the biggest contribution to U1. So as a result, we obtain that U at this approximation, which is U0 plus U1, so it's U0 plus U1, which is just 1 over R in the 0 plus first contribution, is approximately equal to the sum of this plus this contribution with AF phi that we have found. So we obtain that this is m squared Rg divided by 2L squared 1 plus E cosine phi, this is just U0, plus U1 following from here, the resonant one. 3Rg cube m to the fourth E divided by 8 L to the fourth phi times sine of phi. But note, this term in our approximation is much smaller than this one. So this is just a perturbation. So then this expression, let me write it like this. This expression can be approximately equated to, so we approximately, well, let me write that this, from this follows that R0 plus 1 is approximately equal to m squared times Rg divided by 2L squared times 1 plus E cosine phi minus 3Rg squared times m squared over 4L squared phi. So this term is much smaller than this term under cosine. So if we Taylor expand the cosine, from here we just obtain this. So from the expansion of this term, we obtain this term. So this expression is just approximately equal to this one. But when we have written this correction in this form, we can make the following observation. Before this correction, the trajectory was closed. Was closed like this. It was R0 at phi was equal to R0 at phi plus 2 pi. Well, that's easy to see from this expression. U0 at phi is equal to U0 plus 2 pi, phi top plus 2 pi. So R0 is closed. But now, due to this extra correction, the trajectory is closed under the following condition. Under the condition that R0 plus 1 of phi is approximately equal to R0 plus 1 of phi plus 2 pi plus extra contribution due to this term, plus 3 pi Rg squared divided by 4 L squared m squared. So there is a precession. So the particle doesn't go back, but a little bit shifted by a small angle following from here. So the angle follows from here. So we have, let me remind you, we have arrived at the following statement, that u0 is equal to 1 over r0, which is m squared rg 2l squared 1 plus e cosine phi. At the same time, u0 plus u1, which is 1 over r0 plus 1, so it's a 0 level plus first correction, is approximately equal to m squared rg divided by 2l squared 1 plus e cosine of phi minus 3 rg squared m squared 4 l squared times phi. So while this guy corresponds to closed trajectories, so r0 of phi is equal to r0 plus phi plus 2 pi, so this is closed elliptic trajectory. This guy corresponds to not closed trajectory, so so we have r0 plus 1 of phi is equal approximately to r0 plus 1 of phi plus 2 pi plus small correction due to this term, which is 3 pi rg squared m squared 2l squared. So we have a precession. So the trajectory is not quite closed. So there is a small rotation by an angle falling from here. The rotation angle is just 3 pi rg squared m squared over 2l squared. So in the case of circular orbit, if we have circular instead of elliptic orbit, L just in non-relativistic limit, just mvr, where mass, m is the mass of the planet, v is its velocity, r its radius, and we also have that v squared is equal to rg over 2r. So then, for this case, from here, we find that delta phi is approximately 3 pi rg over r. So this is for the circular orbit, while for the elliptic orbit, delta phi, in similar manner, one can find that delta phi is approximately equal to 3 pi rg divided by r 1 minus e squared. So let us, the closest planet to the Sun is Mercury. And then we expect, because for Mercury is R, although is much greater than Rg, but still is closest, has closest value to Rg among all the planets. So the Mercury is expected to have the biggest contributions of this sort. Then if we represent, substitute for the values of these expressions for the Mercury, we find that for the Mercury, delta phi is approximately 10th digit of the second, angular second. So it's 0.1 of angular second. But this is a secular effect, so it like grows in time, and during a century, during 100 years, it goes up to 43 seconds. And this is already a measurable effect, and it is measured and is in perfect agreement with the discrepancy that was observed for the Mercury more than 100 years ago.